Hey everybody, welcome back. Thrasher here. In this video, we are kind of expanding on the last topic, which is gravitational force, but we're going to look at something known as a force field, kind of define what that is, and see what they are. It turns out, spoiler, they're a diagram, so most of this video is going to be walking through how to make these diagrams, alright? Now, we learned about the gravitational force in the last video. Anything with mass is attracted based on how massive those objects are and how far away they are. Classically, this is done for like astronomical objects like the moon and the earth, the sun and Jupiter, black holes and distant galaxies. I mean, you could kind of do it for anything, but it's all about that gravitational force. Remember, that force is weird. Nearly every force we experience requires contact, a kind of push or a pull, one thing touching, maybe pressing upon or otherwise in contact with another. But gravity is different. It does not require that contact. We say that gravity acts at a distance. But that lends itself to a problem. Like, if I said, like, Sally kicked the ball, you obviously know where those forces occur. It was Sally and it was the ball. It was super obvious. But gravity, not only does it act at a distance and therefore kind of all around us, there's no contact needed. So you don't know exactly where it is. It makes it tough to visualize. So this bullet point, how can we represent where and how that force is acting? Well, that leads us to the topic of our video. In physics, we use fields, this term fields. What it does is it represents forces that are acting over distances, okay? Now, in physics, a force field is simply a region where a force acts. I know that force fields have a lot of ideas or interpretations in sci-fi, and I'm sorry to say that it's fairly disappointing what an actual physics force field is. A force field is a diagram, it's a kind of picture that represents the strength and the direction of a force, say of gravity acting on objects, okay? It's not super special, it's not even admittedly super interesting. It's a way to visualize how forces, the ones that act at a distance like gravity, how strong they are and in what direction they're maybe pulling on objects. An analogy, it's maybe not an amazing analogy, but temperature is something we don't obviously see with our eyes, okay? If I look out the window, it's tough for me to just know what the temperature is. I can maybe give a range, but if you watch the weather person has a weather map, and it shows a region, and it identifies, numerically in this case, the temperature, so we can see in different locations how strong temperature is. A force field is similar. It is a diagram that represents how strong and also the direction of gravity at different locations, okay? To be honest, the best way to learn how you draw these is to just do it. So here's my scenario. I kind of have a nice open field, and what I'm going to pretend to do, it's maybe going to sound silly, pretend that I reached into my pocket and I pull out a little mass, okay? I have it on my computer screen like a little black dot. Maybe it's a rock, maybe it's just some small particle. I'm holding up in front of my camera a bolt. I'm not going to do this the whole video, but imagine I just reached into my pocket. That's why I have this pant pocket diagram here. So I reach into my pocket, I pulled out a little mass, and let's just say I was holding the mass up in the air just like this, and it's on my screen here. If I'm holding this mass, if I let go, what direction do you think the force of gravity is acting on this object? What do you say? If you thought down, fantastic, not a trick question. Gravity pulls things downward, so a little mass would feel a downward force. Let's repeat. Let's pretend I again reached into my pocket, I pulled out another mass, and now I'm holding it over here. What direction do you think the force of gravity is acting? Also down. Okay, I reach into my pocket, I pull out another mass. What direction do you think it is here? Also down. I reach into my pocket again, I pull out a fourth mass. What direction? Okay, one more, okay? Let's say I reach into my pocket, I pull out a final mass. Oh, now I'm holding it directly above the one before. What direction is the force of gravity on this object? It's also down. Okay, I'm sorry. This is not the most interesting of things. We learned that gravity pulls things down all around us. Walk anywhere in your local neighborhood. Drop an object, gravity pulls it downward. This is a small diagram showing the force of gravity, the direction and how it acts on objects. Now, team, I'm lazy, okay? maybe you recognize if I have an object anywhere here and I let it go, it's going to fall downward. So instead of drawing a bunch of little arrows, I could draw one longer arrow. Because if I dropped an object here, or if I had my little object here, it would feel a force downward. So in fact, that's what we do. We pretend we're placing these little objects. You'll often hear me say, pretend you reach into your pocket and pull out a little mass. But you pretend that you're releasing them in different spots. These arrows represent the force field. Here on planet Earth, because I'm so sorry, it's kind of boring, gravity pulls things straight down, you would represent the force field by drawing downward arrows. That's kind of it. Now, I know there's text here. Don't look at this quite yet. Don't worry, we'll talk it over. Look over here. Let's imagine now that we're not on the surface of the Earth, but now we're zoomed out. Earth is a sphere. It's basically a sphere, okay? Now, some people live in like Australia in the southern hemisphere. Obviously, they don't fall down. We saw that gravity pulls things inward, technically toward the center of the Earth. That's why even though some people might be in the Arctic, some people might be in Central America, some people might be in New Zealand, they're not falling away from the Earth. Gravity's pulling them toward the center. This is maybe ever so slightly more complicated than this diagram, but again, let's pretend I reach into my pocket, I pull out a little mass. If gravity is always pulling things toward the center of Earth, then whether I release that mass here, or over here, or over here, it's being pulled toward the center. So the line should now be pointing toward the center, okay? So this is the gravitational field for the Earth, zoomed out a little. This is the force field when we're like on the surface. There are technically rules. I'm not like super nitpicky, but we should try to, in general, follow these guidelines. These 4 statements just help us keep our diagrams fairly organized, so they're not super chaotic. The force field lines, they include an arrow. That is crucial. If you do not include an arrow, you are not going to get full points on one of my quizzes because the arrow tells us the direction of the force. Gravity pulls things inward towards their center. So these lines should not have an arrow going away. That doesn't make sense. The arrows are inward. It says that lines can curve, but they shouldn't cross each other. To be honest, that's just something scientists decided to help keep our pictures nice and relatively organized. So we're not going to have lines crossing. It doesn't really make sense to do it here or in this picture anyway, because gravity isn't making them move side to side, okay? But in general, we don't want the lines to cross each other. Technically, number 3 is not super crucial, but to keep our diagram nice, these lines are always touching my object at perpendicular angles at 90 degrees, all right? So we try to do that, again, just to keep things kind of nice. Also, in general, this is usually true when you have multiple objects in your picture, which you'll see an example of. But if you have more lines, more arrows, that usually is meant to represent a stronger gravitational force. If there was another sphere nearby that we said had less mass, less gravity, you might draw fewer lines, okay? But to be honest, just reading these 4 isn't super helpful. We're going to do one more example, and then obviously if you're in a physics class, you're going to do more practice. Okay? Now, it's worth mentioning before we do our last example that whenever I'm talking about like this little mass wanting to move downward, we're talking about the force of gravity. And it comes from this equation that we learned before. The force of gravity is based on the mass and distance. That means if you have an object with a lot of mass, there's a lot of gravity. A smaller mass, less gravity. Okay, it also means that force is based on the distance. We're kind of pretending like we're reaching into our pocket and pulling out a little mass. So that's one of these masses. You kind of think, how big is the other thing? Or if there's multiple objects, how big are those other objects, okay? Now, to be honest, I'm going to show you one other diagram. It's going to spoil it. It's going to show you the gravitational field, but we're going to make sure we understand why the diagram that's drawn makes sense, okay? This is showing the gravitational field between Earth, right here, and the moon. These bluish arrows, kind of bluish purple arrows, these are representing the gravitational force field for when there is both the moon and the Earth together. Why do these lines make sense? We're not going to go over every line. That'd be crazy. But let's go over a few to see if it makes sense to us. Let's pretend I was over here, okay? It's going to sound silly, but this is my mantra. I'm pretending to reach into my pocket. And let's say I pull out a little mass. For these pictures, maybe it's helpful to think of an astronaut, but it's really just like a little test mass. If I had a little mass and I had it right here, right there, and then I let go, what direction do you think the force of gravity would move an astronaut, or would move a little mass that was placed right here? Well, you learned that gravity is attractive. There's the Earth, which is gigantic nearby. So, an astronaut placed right there, or a little mass placed right there, they would feel a force and they would attract toward the center of the Earth. That's why this line is correct. There's an arrow pointing to the left because the Earth, and in fact also the Moon, is directly to the left. They are pulling on my mass, okay? What about like right here? If I had a little mass right here, does this line make sense? Probably, because again, if I had a little astronaut, the Earth is giant, it has a large pulling force on my astronaut, it would pull them down. Now, let's swing on over here. If I had my astronaut, or if I pretended to reach into my pocket, pull out a little mass, and I put it right here, this line's going to the Moon. Does that make sense? Yeah, because the Moon has mass, it is a distance away, it applies a force. The Moon attracts objects as well. They drew fewer lines here to represent the fact that the Moon is smaller. It's less massive than the Earth. Less massive, less force of gravity, fewer lines. That was one of our rules from those 4 bullet points earlier. There's only just a couple more I want to focus on. Look at this line. This line's a little interesting. This line is curving. Before this picture, all of our other lines were straight. Does this line make sense? And it should, because let's pretend to reach into our pocket, take out a little mass. Let's put that mass right here, okay? That little mass is going to feel a gravitational force from 2 things. This mass is attracted to both the Earth and the Moon. That's why we're not going straight to the Moon. If there was only the Moon in the picture, the line would look something like this. But the Earth is also tugging on our astronaut. So at first, they're kind of like going between the 2. So they're being pulled by both objects, and then when we get to right about here, notice the line is curving. Why does that make sense? Can you rationalize it in your head? Even though both the Earth and the Moon are pulling on my object, maybe my astronaut, and yes, it is true that the Earth is bigger, I'm a lot closer to the Moon. The Moon, it kind of like it wins this tug of war. Even though there's this other thing, because I'm closer to the Moon, yoink! The Moon wins. Here's a silly analogy. Let's pretend these are 2 bowls of candy. I love candy. Let's even say that this is a bigger bowl of candy. So all else being the same, I would rather go to a big bowl of candy. So here I am standing over here. I see in the distance there are 2 bowls of candy. I'm attracted to both because I love candy. But when I get to about here, even though this bowl is nice, I like it, even though it's even bigger, I'm really close to this bowl of candy. So, I'm a lazy person. I would rather go to the nearby bowl of candy. That's where distance can come into play, okay? So that's why sometimes the Moon can kind of win the tug of war. But if I'm even a little closer to the Earth, this line, again, I'm attracted to both. I like both things. But we can't forget that the Earth is also really, really big. So in general, the Earth is stronger. So this little mass, this astronaut would actually be curved over here. Team, there's not just one right or wrong way to do this. This is kind of artistic. It kind of lends itself to your interpretation, what you think is best going on. So don't think there's always simply one best way to draw these. But what are you doing? You're pretending to reach into your pocket, pull out a little mass, pretend like you're going to place it in different areas, and then pretend to draw how that force of gravity would act. Couple of things. Again, it's kind of artistic. This is as close to being artistic as I'll ever get because I have very poor artistic abilities otherwise. But there's often a bit of symmetry. Notice there's very similar things happening up here compared to here. In fact, a lot of stuff is going on similar over here, similar stuff over here. weird at first. This is, of course, one of those things where you get good at it by doing practice problems. This is definitely kind of a weird topic. Here I am on my last slide, just going over what I often give my students. So it's not like you're expected to memorize these. If you jotted down notes, fantastic. That helps you internalize things. But we will be given these kind of list of rules. And of course, because it's weird at first, you'll get practice drawing these. Certainly if you're in my own class, and probably if you're taking another physics course some way, somehow. But that's all I got. Thanks a lot for watching this video.